Have you ever wondered about which climate change scenario to use for your climate risk assessment? We hear many different opinions about this, and at times the debate can be heated. Some folks believe that this choice is a big driver of risk treatment costs, and they pressure us to use less emission-intense scenarios, mostly because they are less intense. This is all well and good, but before we can even express an opinion on this matter, we all must understand what the different climate projections represent. Once we're on the same page, it's much easier to select projections that are realistic and best align with the owner's objectives. In this tutorial, we return to first principles and examine the foundation of the different climate projections. For most of our work in climate risk assessment, we relied on representative concentration pathways, or RCPs, to define projections of the future climate. Projections cover a wide range of possible futures, and each possible future has its own unique set of climate risks. RCPs form the basis for climate change projections for the IPCC's Fifth Assessment Report, issued in 2014. They are denoted by a set of numbers. Often, these numbers are thrown around without any clear understanding of what they actually mean. RCP identifier numbers indicate the change in atmospheric radiative forcing since the year 1750. So what is radiative forcing? By definition, radiative forcing is the difference between the amount of energy reaching the Earth and that which the Earth radiates away is infrared radiation. Let me explain. Solar energy is emitted by the sun. A portion of this energy reaches the Earth. Some of that simply bounces off the surface of the Earth back out into space. Some bounces off clouds. Some reaches the surface and is absorbed. The Earth, in turn, re-emits absorbed energy in the form of infrared radiation. And this is where it gets interesting. Infrared radiation interacts with greenhouse gases in the atmosphere. This causes the greenhouse gases to heat up and share that energy with the surrounding environment. This is the greenhouse effect. And we've always had a greenhouse effect. It makes life as we know it possible. Without it, the average global temperature would be minus 18 degrees Celsius. With it, the average temperature is about 16 degrees Celsius. Since the Industrial Revolution, we've been adding increasing amounts of greenhouse gas to the atmosphere, with an associated increase in the greenhouse effect. But by how much? And this is where climate scientists introduced the idea of radiative forcing. Radiative forcing is the difference between energy in and energy out compared to the year 1750, a stable baseline prior to the Industrial Revolution. In climate modeling, scientists assume a radiative forcing for the year 2100. From there, they can calculate different climate projections. The basis for each projection is a radiative forcing value, which is indicated in the description of the projection. In this way, RCP 1.9 represents a case where the radiative forcing in 2100 is 1.9 times that of the year 1750, and so on. Larger radiative forcing values represent a change in the balance of energy retained by the Earth's atmosphere since 1750. The larger the number, the more retained energy. Larger values translate into more global warming. For our purposes, the key takeaway is that larger RCP identifier values mean more climate change. Each RCP projection has embedded assumptions that we should consider before we land on a specific RCP for our assessment work. RCPs are derived from projected greenhouse gas concentrations in the atmosphere. Generally, they do not consider detailed scenarios regarding how those concentrations may arise. Merely, if the atmospheric greenhouse gas concentrations reach a specific level, these are the outcomes we could expect. From there, climate scientists can project climate conditions that would arise. RCPs are stated in units of watts per square meter. And here are the 7 RCPs that are generally considered in climate change work. RCP 1.9. This is the lowest emission pathway. It focuses on limiting warming to below 1.5 degrees Celsius by the end of the century. Radiative forcing is limited to no more than 1.9 watts per square meter above pre-industrial levels. RCP 2.6. Radiative forcing peaks at 3.1 watts per square meter before returning to 2.6 watts per square meter by 2100. This scenario represents a shift to renewable energy sources. Atmospheric CO2 remains at today's level until the year 2020 and then declines. CO2 concentrations peak by 2050, followed by a modest decline through the year 2100. RCP 3.4. An intermediate pathway between the very stringent RCP 2.6 and the less stringent mitigation efforts associated with RCP 4.5. RCP 4.5 is another intermediate stabilization pathway. Radiative forcing is stabilized at approximately 4.5 watts per square meter after 2100. RCP 6.0. Yet another intermediate stabilization pathway. Radiative forcing is stabilized at about 6.0 watts per square meter after 2100. These last 3 RCPs contemplate humankind taking actions that result in stabilizing and reducing greenhouse gas emissions. This assumption is embedded in the scenarios. Beyond this point, the scenarios contemplate failure to mitigate greenhouse gas emissions, and based on actual monitored emissions, they also represent the best estimates of our current trajectory. RCP 7.0, the medium to high end of the range of future emissions, and this arises from no new climate policy. And finally, RCP 8.5, the high-end pathway. Radiative forcing goes above 8.5 watts per square meter by 2100 and continues to rise for some time after that. While RCPs contemplate the sorts of initiatives that could contribute to radiative forcing, they do not consider the socioeconomic conditions that could drive those initiatives. This is the focus of the SSPs, which were developed for AR6. SSPs represent scenarios or storylines that could affect policies and actions that affect radiative forcing. I will go into this in more detail in Part 2. IPCC introduced the concept of shared socioeconomic pathways, or SSPs, in AR6. SSPs are scenarios that could result in increases in greenhouse gas concentrations in the atmosphere. SSPs answer questions about how radiative forcing could reach specified levels. RCPs, on the other hand, answer questions about the effects of radiative forcing reaching those levels. SSPs and RCPs work hand in hand to help climate scientists prepare projections of possible future climate conditions. Shared socioeconomic pathways are narratives or storylines that describe possible development pathways. They consider the social and economic factors that drive fossil fuel use. These pathways explore a range of technological, socioeconomic, and policy futures, and how these factors contribute to potential future climates. SSPs represent possible changes in population, economic growth, education, urbanization, and the rate of technological development that would affect greenhouse gas emissions, providing a storyline of how we could reach certain levels of warming. SSPs are closely tied to RCPs, which are based entirely on greenhouse gas concentrations in the atmosphere. RCPs tell where we could end up without helping us understand the path we took to get there. SSPs help us understand the possible paths to that future. SSPs and RCPs can be used by policymakers to plan for the type of future they hope to create. In our work, they help us understand the basis for the projections we use to do climate risk assessments. Both SSPs and RCPs have numbers associated with them. Example, RCP 4.5 or SSP 5-8.5. The numbers represent the expected change in radiated forcing from the year 1750 to the end of the 21st century. 5 SSP scenarios spanning the range of plausible climate futures were outlined in AR6. SSP1, Sustainability. In this pathway, there are few challenges to both mitigation and adaptation. Policies target human well-being, clean energy, and preserving the natural environment. SSP2, the middle of the road. In this pathway, there are moderate challenges to both mitigation and adaptation. This storyline follows a path of balanced energy development. SSP3, Regional Rivalry. In this pathway, there are many challenges to both mitigation and adaptation. This scenario relies heavily on fossil fuels and an increased use of coal. Nationalism drives policy, and focus is placed on regional and local issues rather than on global issues. SSP4, Inequality. This pathway follows a similar energy future to SSP1. It is defined by many challenges to adaptation and a few challenges to mitigation. SSP5, Fossil-Fueled Development. In this pathway, there is heavy reliance on fossil fuels, including coal. This is characterized by many challenges to mitigation and few challenges to adaptation. Based on these storylines and the RCPs developed for AR5, the IPCC has published a range of possible greenhouse gas futures. These futures each have unique climate change risks. As such, climate risk professionals must often select the most appropriate projections to support a system owner's objectives for an assessment. And here are the greenhouse gas emission projections for each of the relevant SSP storylines. We start by looking at the historic growth in greenhouse gas emissions from 1950 through 2020. We can see the constant growth in emissions through that period, following a consistent trend since the beginning of the Industrial Revolution. These results are measured and not generated from models. As such, they represent our best estimate of real-world greenhouse gas emissions. From here, we start to plot greenhouse gas emission projections based on SSPs and RCPs. SSP1, the Sustainability Pathway. IPCC offers two projections here, one based on RCP 1.9 and one on RCP 2.6. These are very optimistic storylines that suggest a significant decrease in emissions starting in 2020. SSP2, the middle of the road. Here we get one projection based on RCP 4.5. And even in this storyline, emissions start to rapidly decline after approximately 2050. SSP3, Regional Rivalry. This projection is based on RCP 7.0. This is a reasonably aggressive storyline that is becoming more commonly used in climate risk work. SSP4, Inequality. This projection is based on RCP 3.4. Once again, we return to a very optimistic projection that tracks along with the two SSP1 projections. Finally, SSP5, Fossil Fuel Development. This projection is based on RCP 8.5 and covers the high end of greenhouse gas projections. SSP5 8.5 and SSP3 7.0 generally trend along the same trajectory as historic emissions. SSP 2-4.5 follows approximately the same trajectory between 2020 and 2030, but becomes very optimistic in the following years. Finally, SSPs 1 and 4 are extremely optimistic and show a dramatic decrease in greenhouse gas emissions immediately following the year 2020. So what does this all mean to us as climate risk assessors? First and foremost, we need to be aware that each SSP and RCP have embedded assumptions, and those assumptions cover a very wide range of possible futures. The scenarios are not equivalent. Choosing the right one is more complex than simply reaching into a basket and going with whatever you pick out. Considerable thought should go into these decisions. I was once told that assessors should simply use RCP 4.5 because it uses less intense climate projections and it generates much less aggressive risk profiles. That's to say, it's less expensive to do risk mitigation work when the calculated risks are smaller. But this approach appalled me. It suggests that we can simply do the assessment work in a way that keeps treatment costs down. While this may seem to make sense, it speaks to a clear failure to understand what these scenarios actually mean. I suggest a much more robust risk management approach. First, we need to understand the plausible risk futures based on the current policy environment and how well humankind is actually doing in managing greenhouse gases. That is, which of the SSP pathways best align with observed trends? That pathway should be our bare minimum risk metric. And despite all of our efforts, humankind has not significantly reduced the rate of greenhouse gas emission growth. There has been little change in our emissions trajectory. We still depend on fossil fuels, and some countries are still heavily reliant on coal. The less emission-intense SSPs do not accurately reflect reality. So what should we do in our risk assessment work? I suggest a very conservative approach that incorporates as much of the possible risk as we can. So I lean heavily towards the higher greenhouse gas emission pathways. These seem to best reflect our current trajectory. Even if we start to turn things around, the climate will take a long time to respond to these actions, and we'll still see more intense and more frequent weather events. With this in mind, I usually recommend using SSP 5-8.5 as the starting point for any climate risk assessment work. Some assessors may use RCP 7.0, but the pathways pretty much overlap over the next couple of decades, and that choice has no real impact on risk profiles in the near term. Generally, best risk management practice will identify the most reasonable amount of risk. Then, system owners can decide how much of that risk they can afford to treat and how much they can simply accept. This is risk tolerance analysis. As assessors, we have an obligation to provide our clients with our best estimate of the true risk they are facing. With this in hand, the owner can determine how much risk they will treat and how much they are willing to bear. If we don't give them a complete picture of their risk, they'll be relying on flawed assumptions. But they're still facing real risk, and flawed assumptions lead to inappropriate risk management actions. This is not only troublesome, but it's potentially a liability both for the owner and also for us as risk assessors. As risk assessment specialists, it's our obligation to provide the best advice possible. Selecting climate projections that underestimate the most likely emissions trajectory is providing bad risk advice. Does this mean we should never use less intense climate projections? Clearly not. However, when we do, we need to provide a clear-cut justification for that choice, based on evidence and best reflecting the system owner's objectives. And these objectives may consider the impacts of less intense emission scenarios. But all of this should be augmented by reference to a more realistic SSP, like SSP 5-8.5. There is more to this than simply picking an easier path. While we are basing our work on models and projections, the risks are real. We must provide the system owner with the best possible information to make informed risk management decisions.